Hi, my name is Ricardo. I am from the National Microelectronics Institute.
Hi, my name is Marc Codina. I'm from Universitat Autònoma de Barcelona. We are going to present our project for InnovateFPGA 2021.
Let's start with an overall view of the system by giving a brief description of its components. Our system consists of a CO2 gas sensor, provided by Analog Devices, that uses non-dispersive infrared spectroscopy to measure the concentration of carbon dioxide in the ambient. The analog signals coming out from the sensor board are converted into digital samples and sent to the NEOS 2 soft processor. To compute the estimated CO2 levels, the processor uses a simple algorithm based on the Beer-Lambert law for light absorption in gases. We can use the debug console through the JTAG port to print the values computed by the program running on the NEOS 2. The result of the readings is stored in a memory that is shared with the hard processing system in our Intel FPGA. Another process running in the ARM core is the one that sends the CO2 readings via Ethernet to the Microsoft Cloud servers, where they can be managed by the final user with specific data analytics tools. This is a view of the Platform Designer tool available in Quartus. We have reused an example project from Intel to build our system where we have just added the IPs required for our application, in this case, an ADC controller and a GPIO to modulate the light used in the sensor with a 5 Hz square signal. Once we generate the system with the Platform Designer and assign the corresponding pins to the new connections, we are ready to go to program the Intel FPGA. The C program that computes the estimated CO2 level from the digital samples is already running in the NEOS 2 processor. We can use the debug console to display the calculations in real time as they come out from the sensor. The readings from a variety of sensors located in the RFS daughter board also show up on the console screen, as we are reusing a reference design intended to do so. At the same time, we can check how the HPS system is already sending data messages to the Microsoft Azure Cloud Server, with the help of another debugging console connected to the ARM processor through the UART port. All the systems are up and running, and our CO2 sensor is continuously doing readings nearly every 2 seconds. We can check now in the Azure server that the graph plotting the CO2 readings is also updating properly with new values. With everything in place, we are going to test further the capabilities of our system. We light a candle that will guide our next steps. We are going to produce carbon dioxide with 2 very common ingredients that anyone can find at home: vinegar and baking soda. We just mix them using arbitrary quantities to achieve a good reaction. Carbon dioxide is heavier than the air, so it will stay at the bottom of the bottle. Since it is a colorless gas, we cannot see how much gas is produced. Now we pour the CO2 gas into another recipient. It takes a little imagination to believe that we are actually pouring an invisible gas into this empty cup. To check that the plastic cup is full of gas, we are going to pour it over the candle. If so, the CO2 gas will displace the oxygen and the candle will be extinguished. Bingo! Let's pour now the rest of the gas over our sensor and check what we see in the graph running in the Azure server. As expected, a sudden rise in the CO2 levels can be observed in the graph. We opened the windows to ventilate the room after our vinegar experiment, and tried another fairly well-known but effective source of carbon dioxide. This time we obtained an even greater increase in CO2 levels. With these simple experiments, we were able to demonstrate that our system works quite well. We hope that you enjoyed our video demonstration. Thank you very much for your attention.